In this lesson, we will concentrate on the general performance principles of an aeroplane in the en route phase of flight. Performance in the en route phase can be measured using the aeroplane's range and endurance parameters. These will be discussed in detail later on in the lesson. Let us firstly examine the forces acting on an aircraft in the cruise. These forces are split into couples. The first of these couples is produced by lift and weight. Weight acts through the center of gravity of the aeroplane directly towards the center of the Earth. Lift balances weight and acts through the center of pressure, shown here. The effect of this couple on the aeroplane is to cause a nose-down pitching moment. The lift-weight couple is comparatively strong, and thus the nose-down pitching moment is large. As an example of the size of these forces, in a 737-800 series, the maximum structural mass is 79,000 kilograms. At this mass, the aeroplane weighs around 770,000 newtons. Obviously, this weight will be balanced in cruising flight by an equal and opposite lift force of 770,000 newtons. The second couple acting upon an aeroplane in flight is that produced by the forces of thrust and drag. The effect of this couple is to cause a nose-up pitching moment. Notice, though, that this couple is far weaker than the lift-weight couple. The maximum thrust produced by the engines of a 737-800 is only 214,000 newtons. This means that the nose-up pitching moment does not balance the stronger nose-down pitching moment of the lift-weight couple. As a result, there is still a nose-down tendency. In order to maintain level flight, we need somehow to generate an opposite moment which will balance the residual nose-down pitching tendency. This is achieved by the tail plane, or horizontal stabilizer, on the aeroplane's tail assembly. The horizontal stabilizer, or tail plane, must be set at an angle which will cause a nose-up pitching moment to balance the aeroplane, or, more commonly expressed, to trim the aeroplane. Notice that now the nose-up and nose-down pitching moments are in balance and level flight is possible. The downforce generated at the tail is called tail plane downforce or tail load. Although such a force is necessary for level flight, it does have two adverse effects on aircraft performance. Firstly, notice that the tail plane downforce acts in the same direction as weight. It therefore increases the effective weight of the aircraft. The second adverse effect of the tail plane downforce is its contribution to drag. The tail plane is an aerodynamic surface designed to produce lift. It will, therefore, produce induced drag as well as parasite drag. Therefore, the greater the amount of balancing force produced by the tailplane, the greater the airplane aerodynamic drag. We will shortly understand that the two additional forces provided by the tailplane are detrimental to the airplane's en route performance in terms of range and endurance. To some extent, the amount of tailplane downforce required for level flight can be manipulated by changing the center of gravity. In flight, this can be done in one of two ways. Firstly, by selective fuel consumption, or secondly, by fuel transfer. Consuming fuel in the tail first, or transferring fuel out of the tail to other tanks, will move the center of gravity position forwards. Conversely, using fuel in the center or forward tanks first, or transferring fuel out of these tanks will cause the center of gravity to move aft. If the center of gravity moves forwards, the magnitude of the lift-weight couple increases because the arm of the two forces is now longer. This increases the nose-down pitching moment. To balance the nose-down pitching moment and maintain level flight, more tailplane downforce is needed. You may recall that this had the effect of increasing the weight and drag of the airplane, which would have a detrimental effect on the aircraft's performance, reducing both its range and endurance. If the center of gravity moves aft, the strength of the lift-weight couple is decreased because the arm of the two forces is now shorter. This decreases the nose-down pitching moment. To balance nose-down pitching moment, less tailplane downforce is needed to maintain level flight. Reducing tailplane downforce reduces drag and effective weight, which will increase both the aeroplane's range and endurance capability. Remember that, before you fly, when carrying out a weight and balance check, also ensure that the centre of gravity is still within the limits published in the aircraft manual. Be extra careful when handling data produced by countries whose units of measurement are different to those you are used to. This particular section of the lesson will deal with the aeroplane's speed, including maximum speed, minimum speed, and the relationship between the various expressions of speed such as indicated airspeed, calibrated airspeed, true airspeed, true ground speed, and Mach number. Firstly, let us examine what we mean by an aeroplane's maximum speed. You will have learnt from earlier lessons that an aeroplane will remain at a constant speed when the forward and rearward forces are balanced, as shown here. In this case, thrust is equal to drag. In order for the aeroplane to accelerate, thrust must exceed drag. This can be achieved by the pilot opening the throttle further to increase power. With thrust greater than drag, the airplane will accelerate. As the aeroplane accelerates, drag will increase. When drag reaches a value which is the same as the thrust, then acceleration will cease and the aeroplane will have achieved balanced flight once more, but now at a higher speed. Therefore, the highest level flight speed that can be flown by the airplane will be at a speed where thrust is maximum and drag is maximum. Shown on screen are the thrust and drag curves for a typical jet airplane. Let us look again at what we have just learnt, but this time using the graphs. Here, thrust is more than drag, and therefore in level flight, the airplane will accelerate. As we explained, drag will increase as speed increases, until thrust and drag are again equal. This speed is the fastest speed the aeroplane can achieve in level flight. Look at the graph again and notice that there is another point on the curves where thrust and drag are equal. This speed represents the slowest speed that can be maintained at a given thrust setting, since thrust and drag are equal. In level flight, it would be impossible to fly any slower at this thrust setting, since the rearward force of drag would exceed the force of thrust. The area to the left-hand side of the bottom of the drag curve is commonly referred to as the back of the drag curve, or the speed region of reversed command. Flying at these speeds is inefficient and not recommended since a lot of thrust is needed to maintain a fairly slow speed. Notice that at high altitude, the thrust produced by the engine decreases. Looking at the graph now, it is clear to see that at high altitude, the maximum achievable level flight speed is slower, and the minimum achievable level flight speed is faster than at lower altitudes. Thus the range of speeds for the airplane is narrower. This next part of the lesson will focus on the explanation of the various expressions of aeroplane speed. Different expressions of aeroplane speed are used for different purposes, depending on whether we are concerned with aerodynamics, operations, navigation, or even performance. In most cases, aeroplane speed is measured using certain types of probes, called the total pressure and static pressure probes, as shown here. These probes help us to isolate dynamic pressure on which indicated airspeed is based. You can feel total pressure by simply putting your arm out of the window of a moving car. However, total pressure probes, sometimes called pitot probes, and static probes suffer from errors. Without any correction to the errors, the speed which is obtained from the probes when dynamic pressure is being sensed is called the indicated airspeed, abbreviated to IAS. Indicated airspeed is the speed that is displayed on the airspeed indicator. If the pressure probes are corrected for instrument and position errors, the speed is called calibrated airspeed, abbreviated to CAS. This speed is also known as rectified airspeed, or RAS, but this expression will not be used on this CD. Calibrated airspeed is more accurate than indicated airspeed. In large, modern commercial airplanes, the air data computer automatically corrects the pressure probe data for these errors and displays the calibrated airspeed in the airspeed indicator rather than the indicated airspeed. The final correction to make to the information received from the pressure probes is the correction to compensate for the effect of compressibility. Typically, at speeds beyond 220 knots, the air ahead of the aeroplane does not move out of the way. As a result, the air starts to build up and compress in front of the aeroplane. This build-up of air has an effect called the compressibility effect. If the probes are corrected for the compressibility error, as well as position and instrument errors, the speed obtained is called equivalent airspeed, abbreviated to EAS. Equivalent airspeed is the most accurate of the speeds which are obtained from dynamic pressure. For the most part, this performance CD will assume that indicated airspeed, calibrated airspeed, and equivalent airspeed are the same. The next speed to consider is true airspeed, abbreviated to TAS. True airspeed is the equivalent airspeed corrected for density error, and as the name suggests, is the true speed of the aircraft relative to the air through which the aeroplane is flying. On screen is a very simplified formula showing that true airspeed is proportional to the equivalent airspeed and inversely proportional to the density. If, for a constant equivalent airspeed, the density were to fall, the true airspeed would increase. This means that with increasing altitude at a constant equivalent airspeed, true airspeed increases, as shown by this graph. True airspeed can be calculated by using the tables in the aeroplane flight manual, using a flight navigation computer, or even using the airspeed indicator. True airspeed is mainly used for navigation and flight planning purposes. The next speed to consider is the true ground speed, abbreviated to TGS or just GS. This represents the aeroplane's speed within a fixed ground reference system. Put more simply, it is the aeroplane's velocity over the ground. The true ground speed is equal to the true airspeed plus the wind component. If there is a tailwind, then the aeroplane's speed over the ground will increase by a value equal to the speed of the tailwind. So, in our example, if the true airspeed is 250 knots and the tailwind is 20 knots, the true ground speed is 270 knots. Conversely, if there is a headwind, the aircraft's speed over the ground will be reduced by a value equal to the speed of the headwind. So, in our example, if the true airspeed is 250 knots and the headwind is 30 knots, the true ground speed is 220 knots. If the headwind or tailwind components are not already known, these can be worked out using a flight navigation computer or by using the supplied CAP 698 manual on page 49, as illustrated here. At speeds higher than about 220 knots, some of the energy of the aeroplane goes into compressing the air ahead of the airplane and locally increasing the density of the air. Compressibility affects the amount of drag force on the aeroplane, and the effect becomes more important as speed increases. As the aeroplane moves through the air, it makes noise simply by disturbing the air. This noise emanates outwards in the form of pressure waves. These pressure waves stream out away from the aircraft at the speed of sound in all directions, acting just like the ripples through water when a stone is dropped in the middle of a still pond. However, as the aeroplane approaches the speed of sound, it actually starts catching up with its own pressure waves in front of it. These pressure waves turn into one big pressure shock wave, which causes a loud big bang, called a sonic boom. The shock wave generated actually buffets the aeroplane and decreases the lift force. Obviously, because of the increasing drag, decreasing lift, and aeroplane buffet, pilots need to know when they are approaching the speed of sound. Shown here is a picture of an aeroplane passing through the speed of sound. The shock wave actually causes condensation, which allows an observer to actually see the pressure wave. These two pictures show the shock waves on military aeroplanes flying at 3 times the speed of sound. The next scene will discuss a specific aeroplane's speed which allows pilots to know when they are approaching the speed of sound. The ratio of the speed of the aeroplane to the speed of sound in the air determines the magnitude and intensity of many of the effects of high-speed flight. Because of the importance of this speed ratio, aerodynamicists have given it a special name called the Mach number in honor of Ernst Mach, a late 19th century physicist who studied gas dynamics. Mach number is not an actual speed as such. It is, as we have already said, the ratio of the true speed of the aeroplane to the local speed of sound. Mach number is best illustrated using an example. To calculate the Mach number, simply divide the true airspeed by the local speed of sound. At sea level in ISA conditions, the local speed of sound is 661 knots. If the true airspeed of the airplane is 510 knots, then using the formula on screen, the Mach number is 0.77. In other words, the airplane is travelling at about 3/4 of the speed of sound. If the airplane were to fly faster, the Mach number would increase. If the airplane accelerated to 661 knots, then its speed would be equal to the speed of sound and the airplane would be at Mach 1. Airplanes flying between about 0.8 Mach and 1.2 Mach are said to be in transonic flight. However, the term supersonic is more commonly known. Supersonic flight describes flight speed above Mach 1.2. The speed of sound varies with temperature. As altitude increases, the reducing temperature causes the local speed of sound to fall. At 30,000 feet, the speed of sound is 590 knots. If the true airspeed of the airplane is kept constant at 510 knots, as a result of the falling local speed of sound with altitude, the Mach number will increase. As the airplane's speed approaches Mach 1, the compressibility and approaching shockwave can have very detrimental effects on the airplane's performance if the airplane is not designed to mitigate such effects. As a result, most commercial airplanes in service today have a limit on the maximum Mach number they are allowed to fly at. This maximum operating Mach number is called MMO. The Mach number of an airplane can be displayed in a number of places in a typical cockpit. Shown here are just a few of these places. Having discussed all the relevant speeds of an airplane, it is important to understand the relationship of these speeds with one another as altitude changes. This is best illustrated on a graph. The y-axis is altitude and the x-axis is airplane speed. If calibrated airspeed, or simply indicated airspeed, is kept constant with altitude, then as density falls, the true airspeed will increase as shown. But if true airspeed increases with altitude, while the local speed of sound decreases, then the Mach number must increase. These lines representing these three speeds can be manipulated to help solve complex problems. If the true airspeed were to be kept constant with altitude, the TAS line would be drawn vertically and the CAS and Mach lines as shown. Now, calibrated airspeed decreases whilst Mach number increases. If Mach number were to be kept constant, the diagram could be drawn so that the Mach line is straight up. Notice that TAS and CAS decrease with altitude. The same can be done with decreasing altitude. If the CAS is kept constant during the descent, keep the CAS line vertical and notice that the TAS and Mach number lines slope as shown. This means that if CAS is constant during a descent, the TAS and Mach number will decrease. To help you remember how to draw the lines, C, T and M always appear from left to right. You can use Britain's favourite food, chicken tikka masala, as an acronym for remembering C, T and M. The next section of this lesson analyses the two cruise performance parameters, range and endurance. When flying for range, we are asking the question, how much fuel will the airplane use per unit distance? When flying for endurance, we are asking the question, how much fuel does the airplane use per unit time? Let us firstly deal with the endurance of the airplane. The endurance of an airplane is the time it can remain airborne on a given quantity of fuel, or, put another way, endurance can be expressed as fuel used over a given airborne time. The only time an airplane will be flown by the pilot for maximum endurance is when the airplane is in a holding pattern over its destination. For instance, when there are long landing delays. In this situation, running out of fuel starts to become a problem. In this lesson, we will define endurance to be the ratio airborne time over fuel used for that time. However, to use this formula, a small adjustment needs to be made, as shown here. This now becomes the formula for specific endurance. The units of specific endurance are airborne hours per kilogram of fuel consumed. The endurance of an airplane is simply a function of its fuel flow or fuel consumption as shown by the formula. An airplane which can minimize its fuel flow will achieve maximum endurance. Therefore, when analyzing the maximum endurance capability of an airplane, it is necessary to understand what controls the fuel flow. You should note that this parameter is different for a jet and propeller aeroplane. Let us examine the jet aeroplane first. Here, fuel flow is a function of the fuel used per unit of thrust, multiplied by the total number of thrust units. Obviously, if it were possible to reduce the fuel used per unit of thrust and the total number of thrust units required, then the total fuel flow would be reduced. Fuel used per unit thrust is most commonly known as specific fuel consumption, which is abbreviated to SFC. This value needs to be small. In other words, the aim is to reduce the amount of fuel used to produce each thrust unit. For a jet engine, this occurs when ambient temperature is very low and engine RPM is very high. This can only occur at high altitude. So, flying at high altitude minimizes the fuel used per unit of thrust. Having minimized the fuel used to produce each unit of thrust, the aim is now to fly the aeroplane using minimum possible total thrust because each unit of thrust requires fuel to be consumed. This problem is comparatively simple to solve. In level flight, the forward-acting force of thrust is controlled and balanced by the rearward-acting force of drag. If drag is small, the aeroplane need fly with only a small amount of thrust. Looking at the formula then, thrust can be replaced by drag since the value of drag is equal and opposite to the value of thrust. To minimize drag, the jet aeroplane simply flies at the velocity for minimum drag. Therefore, VMD is the speed to fly for maximum endurance. In summary then, for a jet aeroplane to maximize its endurance by minimizing its fuel flow, the pilot would fly the aeroplane at VMD and fly as high as possible. The situation with endurance and fuel flow for a propeller airplane is very similar to that for the jet aeroplane. There is just one small difference in the formula we use. Turboprop and piston engines first convert chemical energy in the fuel into power output on a shaft. The propeller then converts that power into thrust. So, whereas for a jet the formula for fuel flow was fuel used per unit thrust multiplied by the total number of thrust units, for a propeller the formula is fuel used per unit of power multiplied by the total units of power. Obviously, to minimize the fuel flow, the fuel used per unit of power and the total number of power units developed must be kept to a minimum. Fuel used per unit power, as you already know, is called specific fuel consumption. This value needs to be small, but for the majority of propeller aeroplanes the value is more or less fixed. However, in very general terms, it is safe to say that for piston engines, specific fuel consumption is a minimum at lower altitudes, whereas for turbopropeller engines, specific fuel consumption is a minimum at middle to high altitudes. Therefore, the only other way to minimize fuel flow is to use the minimum amount of power. This can be achieved by flying at the speed for minimum power required, or VMP. Note that for a propeller aeroplane, it is VMP that is the speed for maximum endurance, whereas for a jet, it is VMD. Having studied how to achieve maximum endurance for both jet and propeller engines, let us now examine what factors actually affect endurance. The first factor we must discuss is the effect of weight. You will recall that increasing the weight of the aeroplane increases induced drag and thus moves the total drag curve and power required curves up and right. Looking at the jet diagram which uses drag, you can see that at higher weights the aeroplane has more drag and therefore requires more fuel flow. In this situation, the endurance will decrease. We must also note that the speed for maximum endurance, VMD, is now higher. For a propeller aeroplane, the situation is similar. For a propeller aeroplane at higher weights, more power is required, therefore, fuel flow increases and endurance decreases, but also the speed for best endurance, VMP, is higher. There is one other effect that is seldom mentioned. At higher weights, operating altitudes are lower, which for a jet aeroplane means that the specific fuel consumption increases because at lower altitudes the jet engine is less efficient. The next factor which affects endurance is the aeroplane's configuration. While it seems an obvious point that the undercarriage and/or flaps should not be deployed in the cruise, there will be occasions when a pilot will find himself stacked with other aeroplanes in a holding pattern over the destination airfield. As the aeroplane at the lowest level exits the hold to land, the other aeroplanes will have to descend to a lower hold and eventually prepare for the landing by deploying undercarriage and flaps. You will recall that deploying the flaps and undercarriage increases parasite drag and thus causes the total drag curve and power required curve to move up and left. Looking at the jet diagram, which uses the drag curve, you can see that with the gear and flaps deployed, the aeroplane has more drag and therefore requires greater fuel flow. But notice that the speed for maximum endurance, VMD, is now lower. For a propeller aeroplane, it is much the same. With gear and flaps deployed, more power is required. Therefore, fuel flow increases and endurance decreases, but also the speed for best endurance, VMP, is lower. Fuel flow in the landing configuration can increase by 150% compared to a clean configuration, so it is important not to deploy gear or flaps too early and unnecessarily increase the fuel costs for the flight. What other factors affect endurance? We still haven't considered altitude or wind. Well, the case of wind is quite simple. It has no effect on endurance. You will remember that maximum endurance is concerned with minimizing fuel flow. Now, it should be obvious that wind does not affect the fuel flow into the engine. Endurance is about time in the air, not distance covered. Whatever the effect of wind on range, an aeroplane will still remain airborne only for as long as it has usable fuel in its tanks. Altitude, however, does affect endurance. Its effect, though, is a little complicated and is very dependent on engine type. Generally, jet aeroplanes become more efficient as altitude increases, partly due to the decreasing ambient temperature, but also because of the increasing RPM required to maintain thrust. Therefore, theoretically, the maximum endurance of a jet aeroplane will be achieved when flying at or above the tropopause, where the ambient air temperature is lowest. Turbopropeller aeroplanes function in a similar way to a jet, since they are, in essence, jet engines with a propeller attached to a geared shaft. However, even though the turbopropeller engine gains efficiency with altitude, the power required increases, offsetting the efficiency gains. This means that for the majority of modern turbopropeller aeroplanes, maximum endurance is achieved at around 10,000 feet or less. Piston engine aeroplanes are most efficient at sea level when the manifold pressure is high and RPM is low, provided that the mixture has been leaned correctly. In summary then, jet aeroplanes achieve maximum endurance at or above the tropopause. Turbopropeller aeroplanes reach maximum endurance at about 10,000 feet. And piston engine aeroplanes have their maximum endurance at sea level. You have learnt that there are two performance parameters in the cruise, range and endurance. Let us now consider range. Range is a more useful performance parameter than endurance, and one that aircraft designers continually try to improve. Whereas endurance is about airborne time, range is more concerned with distance covered, and it is, therefore, sometimes referred to as fuel mileage. Maximum range can be defined as being the maximum distance an aeroplane can fly for a given fuel quantity consumed, or to put it another way, the minimum fuel used by an aeroplane over a given distance. This latter expression of range is more commonly used for commercial operations. As a formula, range is simply the distance in nautical miles divided by fuel quantity in kilograms. However, in the same way as we did for the formula for endurance, we must adjust our range formula needs in order for it to give us useful information. The top line of the formula is air nautical miles per hour, and the bottom line of the formula is kilograms of fuel per hour. Thus, the formula now reads true airspeed divided by fuel flow. This is the formula for specific air range. The formula shows that specific air range is defined as the ratio of true airspeed over the fuel flow. You may recall from the endurance lesson that fuel flow is specific fuel consumption multiplied by drag for a jet and specific fuel consumption multiplied by power required for a propeller-driven aeroplane. Looking at the formulae, it is now obvious that in order to maximize the specific range of the aeroplane, true airspeed must be high and the fuel flow must be low. Let us now focus on the specific air range of the jet aeroplane. We stated earlier that to maximize the range, the TAS must be high and the specific fuel consumption and the drag must be low. Shown on screen is the drag curve for a jet aeroplane. If the aeroplane were to fly at VMD, then of course the drag force would be at its lowest. Referring to the formula, it seems we have solved one of the points, namely how to make drag as low as possible. However, looking at the graph, notice that because the drag curve is fairly flat at the bottom, the speed may be increased significantly from VMD for only a small drag penalty. From the formula, we can therefore see that whilst drag has increased a little, which is bad for range, the airspeed has increased significantly, which is good for range. Consequently, the overall effect is that there is an increase in specific range. The speed at which the speed-drag ratio is maximized may be read from the graph at the tangent to the curve. You may recall that this speed was 1.32 VMD. Therefore, it is 1.32 VMD that is the speed for maximum range for a jet aeroplane. There is now only one remaining item left in the formula which still needs to be resolved. In order to increase range even more, specific fuel consumption must be decreased. You may recall that the only way to do this for a jet aeroplane is to operate at as high an altitude as possible. Operating as high as possible will give us a higher true airspeed for any given indicated airspeed, which again will improve the specific range. Having completed the analysis of range for a jet aeroplane, let us now examine specific air range for a propeller aeroplane. We stated earlier that to maximize the specific range, the TAS must be high and the specific fuel consumption and the power required must be low. Shown on screen is the power required curve for a propeller aeroplane. If the aeroplane were to fly at VMP, then of course its engine would be delivering minimum power required for level flight. Referring to the formula, it seems then that we have solved one of the components, namely to make power required as small as possible. However, at the graph, notice that because the power required curve is fairly flat at the bottom, the aeroplane speed may be increased significantly from VMP for only a small penalty increase in the power required. From the formula, we see that whilst power required has increased a little, which is bad for range, the airspeed has increased significantly, which is good for range. Consequently, the overall effect is an increase in the range. The point at which the speed-power ratio is at a maximum is the tangent point of the curve. You may recall that this speed is VMD. Therefore, it is VMD that is the speed for maximum range for a propeller aeroplane. There is now only one remaining item left in the formula which still needs to be resolved. In order to maximize range even more, specific fuel consumption must be decreased. However, you may remember that specific fuel consumption for piston aeroplanes is fixed, whereas for turbopropeller aeroplanes which use jet engines, the specific fuel consumption decreases with altitude. Having studied how to achieve maximum range for both jet and propeller engines, let us now examine what factors affect range. The first of the factors to discuss is the effect of weight. You will recall that increasing the weight of the aeroplane increases induced drag, and thus moves the total drag curve and power required curve up and right. Looking at the jet diagram which uses drag, you can see for higher weights the aeroplane is subject to a higher drag force and therefore requires a higher rate of fuel flow. This will decrease specific range. However, notice that the speed for maximum range, 1.32 VMD, is now higher. For a propeller-driven aeroplane, it is much the same. At higher weights, more power is required. Therefore, fuel flow increases and range decreases. However, notice too that the speed for best range, VMD, is higher. Remember also that at higher weights, the operating altitudes are reduced, which for a jet aeroplane means that the specific fuel consumption increases, because at lower altitudes, the jet engine is less efficient. One of the most important issues that airline operators need to consider is the choice of the aeroplane they operate. This choice is mainly based upon the required aeroplane's payload and range. These requirements can be best described by going through a typical example. Shown on screen is the payload range graph for a Boeing 777. On the vertical axis is the payload in thousands of kilograms, and the horizontal axis shows the aeroplane range in thousands of nautical miles. On the right-hand side of the graph is a bar chart symbolizing aeroplane mass. Here, the aeroplane is at its dry operating mass, DOM, which essentially means the mass of the aeroplane without fuel or payload. This is shown on the bar chart and by the flashing blue marker on the bottom left-hand side of the graph. As the payload is added, notice that the blue mark moves up the payload axis. Notice too that the total mass of the aeroplane is increasing as shown by the bar chart. However, payload will reach a maximum when either there is no more space on the aeroplane or the aeroplane has reached its zero fuel mass, ZFM. Notice that the range at this point is 0 because no fuel has been added yet. This point is marked as A. Fuel is now added to the aeroplane and the marker point moves to the right, showing an increase in range. Adding fuel can continue until the maximum structural takeoff mass is achieved. This is shown by point B on the graph. Notice that the weight bar on the right is now at the top. Although maximum mass has been reached, it is unlikely that the tanks are full at this stage. To increase range further, more fuel must be added. But since the maximum mass has been achieved, the only way to add more fuel is if some of the payload is exchanged for fuel. Now the marker will start to move down and right. This shows that range is increasing, but the payload is decreasing. Swapping payload for fuel in this way can only continue until the tanks are full, as shown by point C. The only way to increase the range beyond this point, even though the tanks are full, is to remove the rest of the payload. At point D, the aeroplane has full tanks, maximum range, but no payload. In the majority of airlines, the trade-off between range and payload is carried out on initial aeroplane purchase and thereafter during in-flight planning. As a pilot, it is unlikely you will be required to work through these graphs other than to check and confirm the data that has been prepared in advance for you. Another factor affecting the range is the aeroplane's configuration. You will recall that deploying the flaps and undercarriage increases parasite drag and thus moves the total drag curve and power required curve up and left. Looking at the graph for the jet aeroplane and using the drag curve, you can see that with the gear and flaps deployed, the aeroplane has more drag and therefore needs more thrust, and which, in turn, requires greater fuel flow. This will decrease the range. However, notice that the speed for maximum range, 1.32 VMD, is now lower. Looking at the graph for a propeller aeroplane, you can see that matters are much the same. With gear and flaps deployed, more power is required. Therefore, fuel flow increases and range decreases. But also notice that the speed for best range, VMD, is lower. A point always to bear in mind in the cruise is that any increase in parasite drag will be detrimental to range and endurance. Increases in parasite drag can be caused by any number of things such as damaged and misaligned surfaces. The extra drag created by misaligned or misrigged airframe surfaces creates a type of drag called excrescence drag. This can be more than 4% of the airplane's total drag. Careful pre-flight inspection should reveal misaligned or misrigged surfaces. An important point to consider over which the pilot has direct control is aeroplane trim. A pilot must periodically check the aileron and rudder trim, the spoiler misfire, and the trailing edges to ensure that the aeroplane is in trim and is in balanced flight. Monitoring the aeroplane's control surfaces will help to reduce the extra drag and extra fuel consumption that out of trim and unbalanced flight can cause. Lastly, contamination on the airframe from airframe icing can affect fuel flow. This icing will not only change the shape of the wing, making it less efficient at producing lift, but it will also increase weight and drag. All this is detrimental to aircraft performance and will reduce the aeroplane's range.